if necessary, if we get too many. And now, how do I deal with this toolbar? Oh, I'll put this up here. Okay. All right. And also, of course, this is old data, so, and it's kind of made up. So it's not real. I mean, you might want to copy it if you have nothing else to work with, but I don't think it's going to get the right results. And also my zero position, I had to do the same thing up here. You have your degrees plus your minutes divided by 60. And we didn't really have time to explore the plus minus angle, but I'm just going to assume 3 degrees because I think with, even though you got that vernier, I think the major source of error is finding that exact spot where it doesn't, where the line would move and stop and reverse itself. That's my feeling is the greatest amount. And I mean, it's probably not going to make a lot of difference, but it's just so we can go through the exercise of using plus minuses. Okay, so delta is the minimum deviation, of course, is just the angle you read minus the zero position. And yours should be 180. It might be 179 in minutes or 180 in minutes. So you notice the dollar sign so that I always pick off the same zero angle, right? And then once I've got it, I just use the fill handle. Well, in any case, the original one too. I find it easier just to do this and then delete away the ones I don't need. Remember, I mean, you could actually just delete these rows if you wanted to so that they're not there. I just like to keep this more generalized. And I just decided I'm not going to go out of my mind. I'm just going to say 3 degrees here. In fact, I haven't even, I just made up this plus minus. So, how do we yeah, that's quite a propagation. So, yeah, so you can copy what I did here, 0.005, and you'll see I already got started. So that was, let's see, N. So N, this is the hard one. So that's, if you recall from the pre-lab, I thought I saw that equation somewhere here, but okay. I've been working on the lab manual, and yeah, here it is right here. So I added one extra bit where it's 2 times sine of 60 plus delta. See that? You might take a pen quick and write that down. Or I know what to do. I can copy paste it. Don't worry. You don't have to do that. Control C and control paste here. Maybe, there it is. So I am recording. I'm recording locally with my own software. Somebody made a request, and the idea is it's a much higher quality than if I used a Zoom recording. Yeah, where was I? Yeah, here it is. So, can you see that? Should I zoom in on it at all? That's translating 2 times sine of 60, and you need that radians because even though this was written by economists, they did all the angles in radians. That's weird, but they did the histogramming in a different way. Yeah, so I made a new video for the histogramming. I updated the final logbook for interference and diffraction. I kind of dropped the ball on that lab, so I just cut to the basics, cut it short. And then there's this analysis, and I think I owe you, I went over the other radiation analysis videos. There's 3 altogether, and they seem okay. And I just had to make sure there's a report outline for radiation. There's no other report. Would you guys prefer it if I made a final logbook for radiation and a final logbook for Balmer, or just make it all one? One? Yeah, I thought you might say that. It just hit me today that I might make. I don't know, whatever. I might do it in the future because like this is what we're supposed to be doing today, but to me, this is like watching. It's worse than a video game. You're just watching meaningless numbers, so we're not even going to bother with it. You can't see what's going on. And I made a depart. If you look at the original manual, this is a big departure because the way it's done in the original manual is very kludgy. We're doing it in the way you would do in a real lab. We're getting the index of refraction, and you might write this down as well for your final analysis, a final logbook. What we're doing is we're taking our prism and we're calibrating it, and we're measuring the index of refraction as a function of wavelength, basically. Here it's angle, but if we know, or we postulate, but we can demonstrate that if we get the minimum angle, then the index of refraction is a function of that angle. And then by association or by our suppositions, that's also a function of lambda. And then once we do that, we can measure any spectra, and we can compare our data with anybody else. The original technique was just kind of dumb. I don't understand it. Okay, so we calculate all our n's, and unless I have 4 decimal places here, they'll all look kind of the same. And then you drag handle it again and just eliminate the ones you don't need. Excuse me. And, right. And then I just made an arbitrary plus or minus n. Yeah, I mean, I lost the whole week because of being sick, so we'll just, we got to get you guys done so you can focus on your finals. All right, so we want to plot n as a function of 1 over lambda squared. So I select that, and now I hold down the control key, and I select n. And then I go to insert menu, and we get ourselves, there it is. And it's quasi-linear, it's not the best, but I don't even know where this data came from. But you should get something approximately like this. However, I did start looking at some groups' data, and unfortunately, you can see right off the bat, something went wrong. Yeah, I guess they did their subtraction because you see these angles are not greater than 180. But unfortunately, when I plotted their data, this is the n as a function of lambda, which isn't what we want. And this is n as a function of lambda squared. Well, I mean, maybe I shouldn't have connected the dots. That's, always almost always a dumb thing to do. But in any event, yeah, I got to make sure I got real data somewhere. If you let me know if your data looks absolutely horrible, send me a message and I'll send you some real data. Okay, so now let's see, add error bars. So chart design, elements, error bars. Let's see, standard error works. Then I'm over. Okay, so now for Mac users, you don't get this. You can't do it from the right side here like PC users. So we got format, and we got let's see, X error bars, and we just want the X error bars to equal 0. Yep. And then the Y error bars, here we go. And where is, oh yeah, custom, specify values. And here it goes. This is nice. You don't even have to worry about those empty slots. Excel just ignores them. And yay, there they are. You know, they're reasonable looking error bars. You could always, just FYI, if you look at that data, and in this case, we expect it to be linear, simply by looking at the scatter of the data points above and below an imaginary line, right away gives you an idea of what the error is, the overall error, the sigma. Because if I were to take those data points and subtract the fit line, then I would actually have a random scattering, quasi-random, but it would be that they would all be kind of the same number. It's the residuals. If you histogram the residuals, right, that's going to be a bell curve because they're not associated with each other, the measurements, and the width of that bell curve is the error on your measurement. We do it by doing the plus minus slope, but it gets almost the same number. Okay, so now I've made my fit line here. See, I have my fit parameters box here. Let's get this one out of here, get that out of the way. So there's the equation. Here's the fit parameter box. And I guess we could add the chi-squares in there so we can get a plus minus slope. Insert. Move cells to the right, and then some CHI squared. There we go. And let's see. So you see S4, in my case, dollar signs, then way back here to the particular 1 over lambda squared, and then the y-intercept. Does anybody need me to zoom on this at all? Looks like we're all tapping away. And then, of course, we have our residuals, which is equal to the data n here minus the fit value, enter, and then the res squared equals this raised, let's see, yeah, here it is. And then the chi-square, oops, I don't need a space there. And that's equal, oops, all right, equals to the res squared divided by the plus minus, that's right. And then that has to be squared. Okay. And, wow, I did something wrong. Oh, yeah, right, because that's an awfully small number. Okay, that's all right. In this case, it's not that big of a deal simply because they're all the same. Okay. We would divide by, oh, of course. And then I want to get rid of this one and get rid of this one and get rid of this one. All right. Coolio. All right, so now we can add the fit line onto here. Select data. Add. That's right. Series name is fitline. And the x values are the 1 over lambda squareds. Whoops. And the y values are the fit line itself. And so notice that you may have your graph go nuts right here. Notice the huge number I typed in here, because I see that 1 over lambda squared is 2 times 10 to the negative 12, and my value of data is 1.6. So if I multiply by 1 times 10 to the 12th, I get 2. So this is, I think, well, it's 1e to the 11th. I'm not sure exactly why that is, but it's close enough. I still would have expected it to be times 10 to the 12th. And then we need to format that to a line. No, wrong one. Format and fit line and paint can and solid line. And as I always like a red one, it's entirely up to you. Oh, and why doesn't it go through all of them? Well, we'll find out. Marker, no. Oh, marker options, none. Okay, let's see what happens. So something is, oh, I see. It doesn't like the empty spots, does it? Okay. You want to be that way? I can play the game. I have a copy of this. Yeah, there, I see the line improved. And I'll get rid of this. And one more. And that. And then line goes all the way. In fact, I could add in all the way to 0. So I should have thought of that. Let's see. One time, so is that already logarithm? No, it's not. Okay. What is this going to look like if I make a 0 there? Okay. The y, oh yeah, because that's the y-intercept, okay. So I always like having the fit line go down to 0, so I can just edit that. Fit line, edit, and then we just select in that 0, and we select in that fit line point, and now it goes to 0. And so now we need equals the sum of the chi-squareds, and close it. It's an awfully large number. And let's see, data, solver, I get all this shit in the way of it. Solver, here we go. The minimum of the sum of the chi-square. And we want to vary the slope and the y-intercept. And we want, yeah, don't constrain it. Let's see what happens. Ooh, wow. Oh, look at that. My error bars came back. Ooh, I thought that would happen. Pretty, huh? Look at that. Wow, look at this. Wow. Remember how huge that was? The chi-square. Wow. Coolio. All right. And does anybody want me to go through finding the error of the slope, or we all feel like we know how to do that?
A lot of this is good with the EM ratio back and forth.
Right, right. So you go back to solver, and well, first of all, you have to copy this sum number, Control C, and then you go to solver, and you tell it to the value of that. I think it can do control. No, it won't let me. Okay, so I have got to, you have to get this number. Let's see what it, so one of the things you do then is you copy this and you paste it as a number. This is a kludge. I gotta talk to these people. So now you see some decimal places. So then you go to solver and you say, all right, make it to the value of 8.402278, and I only want to vary the slope. And yep, and then we solve it, and looks okay. And then we get our extreme of the slope. So then we take this, we copy it, we paste as a number. So now we know the extreme, and now I don't know how to easily go back to the original result. So we minimize it, and we only, well, should we go back to varying both of them? Why not? And then, yep. And we solve, and it looks like everybody's happy. And now we see that the difference between them is dot plus minus. Okay, which looks like 0.05 times 10 to the 10th. All right. So now we've got that. And now we've got our hydrogen data, which is just angles. We don't know the lambdas. And so once again, we have to make this decimal. And we got our minimum angle here. And we'll say once again, it's 3 degrees. Yep. And then so now we use our fit parameters. Okay, give me a minute. No, that's not right. Let's look at the lab manual you just wrote, Harry. Right, so now to get n, we use this guy here. Give me a minute. No, give me a minute. We don't use that guy. So, yeah, if we know the angle, yeah, we get n. We use this guy. So this is, let's copy paste that, Control C, and escape, Control V. I want to make sure I'm doing, right. So then n equals no, I don't believe that because we don't know. What did I do wrong? Give me a minute. I was working on this right before, up till the class. I'm pause the recording, restart the recording. So we use, to get n, we have our equation that we have faith in. We didn't get a chance to independently verify it, but that's not, we just didn't have a good enough spectrometer to do that. So I wanted to expose you to proper technique. And so it's exactly the same as before. And there it is. And this, I don't even know if this is what I want just yet. I'm just going to clear that for now. Okay, and we'll just use our same lame number here. Enter. Okay, so the wavelength measured is going to be blah, blah. This guy. Now we use this one. I used the equation above here with the fit we did, and then, oops, come on, trying to just select, well, let's try that. Control C, and Control V, and there it is. So lambda equals 2, no, I forgot to put the equal sign. Equals SQRT, open parentheses, and I'm going to do another one because I'm going to do the n minus a. And so n minus, and then that's the slope, and it's hidden behind my graph here. No. Oh boy. It's trying to be helpful. I got to get the graph out of the way here. There it is. Okay. Equals SQRT, open, n minus this slope, which has got to have dollar signs, and F4, did it work? Yep. And then n minus a, close that, divide by b, the y-intercept, or did I get it? Oh, wait a minute, b is the slope, okay, so I got it backwards. This is, and it's the slope down below, so this is S5 up here, and divided by the slope. And then that's got to have dollar signs, and then close, and I think that's enough closes, and, whoa. Oh, because of course, if it's, I don't even know what units this is going to be in, but, let's format, and, scientific notation, and okay. Now that didn't work, but that the only thing is, remember, this is data that's not real, so I can't. But I still am concerned that it's not the right order of magnitude. So let's do a double check. If I have n equals b times 1 over lambda squared plus a, then b times 1 over lambda squared equals n minus a, and then 1 over lambda squared equals n minus a divided by b. Oh, and I forgot to invert it. Okay. That equation is wrong. And so that's got to be good. We might be saved here. Back, and that's got to be B, which is, okay, and then on the bottom is n minus delete a. Okay. Yeah, because then we're going to get those 10 to the 12ths on the top. Okay. Let's see, Control C, and Control V. There it is. All right. Is equal. Let's just nuke this. Okay, so square root of b, which is the slope, divided by, open parentheses, n minus a, which is the y-intercept, close it, and is everybody happy? I got an extra parentheses, but I don't think that matters. Still don't like it. Shit. All right, but, oops, I forgot the dollar signs. Okay. Dollar sign here. Dollar sign there. Yeah, I apologize for not having the time to, I've had to catch up with my lecture class too. Okay. Oh, come on. Feature bloat. Yeah, unfortunately, I would have expected this to be negative. Oh, we expressed it in nanometers. Oh, so it's not ridiculously off. Red, right? 700. So I would take that as 740 nanometers, 647 nanometers for greenish. And blue is 563. Oh, so we're in the ballpark. Okay, it worked. I just don't know why the order of magnitude is off there. All right, so what time do we have? Oh, we haven't been in here that long, have we? I have the rest of the analysis is about testing the Balmer relationship. I have that already posted, but what I'm going to do now is I'm going to take this recording. Okay, so I made one key error, and it's over here. It's 1 over lambda squared is supposed to be in micrometers, and I converted it into meters. And so in the spreadsheet you have, it, well, let me pause this a moment. I want to zoom in. All right, so as I was saying, this is supposed to be in micrometers. So micrometers are nanometers divided by 1,000. And I multiplied by 1,000 because I was converting, I must have been thinking I was converting it to meters. So if you put that here and you see the negative 12, right? I was thrown off by that. So if I do it properly, divide by 1,000, then these are much different numbers. And it only changes orders of magnitude. You don't have to, the only thing you have to do now is, so this number used to be 1.9 times 10 to the 10th or something like that. Just see what just type in 1.9 times 10 to the minus 2. And that'll solve all your problems quickly. And then run solver on it. And then notice these work out correctly. They may not be the exact right number, but that's in micrometers. I mean, excuse me, that's in nanometers. So it's kind of a mystery why you convert it to micrometers, but then the answer comes out of nanometers. but it's the first, I just found this, first time I'm doing it. So I'm going to splice this little recording in before you start in on the rest of it.